Quick disclaimer, Learn from Mac is an independent educational project. We are not affiliated with, endorsed by, or sponsored by Apple, or any vendor or product covered in this course. Hey, welcome back to Learn from Mac. I'm Dennis, and today is day 27 of the F5 LTM r4600 Bootcamp. Today we go under the hood of the actual appliance, slot architecture, FPGA offload, and how to safely check and stage a firmware update. Let's get into it. First, the goal. By the end of this lesson, you'll understand the r4600's physical architecture, slot layout, interface naming, FPGA acceleration, redundant power and cooling, and how to safely check and stage BIOS and firmware updates. Here's what you need: SSH or console access to a real r4600, root or admin TMSH access, a valid F5 downloads account for firmware images, and basic HA and VLAN concepts from earlier weeks. Two concepts before we inspect any hardware. Concept 1, slot architecture and interface naming. The r4600 is a fixed 2U appliance with a single traffic processing slot, slot 0, and dedicated port groups following an X.Y convention, 1.1 through 1.8 for 1 and 10 gig SFP plus ports, 2.1 and 2.2 for 100 gig QSFP28 uplinks. This maps directly to what TMSH reports and what you reference building VLANs. Concept 2, FPGA offload, the EPVA. The r4600 integrates an enhanced packet velocity ASIC in an onboard FPGA. When FastL4 or other hardware-accelerated profiles are applied, eligible flows get offloaded from software TMM entirely and processed in silicon, dramatically higher throughput, dramatically lower CPU for bulk TCP and UDP traffic like research data transfers. All right, 3 labs. First, a full hardware inventory, platform interfaces, fan and PSU health, and FPGA firmware status. Then a FastL4 virtual server built specifically to exercise hardware offload, verified by watching the PVA packet counters actually increment under real traffic. Then a firmware inventory and staged update passed through the REST API, checking current versions before ever uploading anything new. Let's get into it. Lab 1, confirm the platform itself first. Physical interfaces and their media type, fan and PSU health, then FPGA firmware status. Lab 2, a FastL4 profile with full hardware offload to the EPVA. A pool and a virtual server built specifically to exercise it, high throughput research data transfer. Send real traffic, then confirm offload is actually happening, not just configured. Lab 3, before touching firmware, check current versions through REST. List what's already installed. Upload the new image before staging it, lest this only stages, it never auto-activates. Confirm the new image is now visible, staged, ready for a real maintenance window. And that's the physical layer of this appliance actually understood, not just abstracted away behind TMSH. There are self-check questions on the lesson page worth sitting with. What actually disables PVA offload, especially since an attached iRule forcing the software path is a common, easy-to-miss cause of why isn't this as fast as it should be? Take a minute with those. Quick recap before we go. Interface naming follows slot.port 1.1 through 1.8, 2.1 and 2.2 on this platform. And it's exactly what you reference when building VLANs and trunks. FPGA offload dramatically cuts CPU for bulk TCP and UDP, but an attached iRule forces the software path even with FastL4 configured correctly. 0 in the PVA counters after real traffic means offload isn't actually happening. Check the profile setting and firmware version before assuming it's working, and always check current firmware versions through REST before ever uploading a new image. Verify what's actually running, don't assume. All right, that's day 27 in the books. Hardware inventoried, FPGA offload verified under real traffic, firmware checked before touching it. That's genuine platform fluency now. If this was useful, hit subscribe so you won't miss a single lesson. Next up is day 28, upgrades, UCS backups, and maintenance. See you there.